Welcome to the 25th lecture video for Physics 4A. We introduce waves in this lecture. As you will hear me say in the lecture, waves are perhaps the most important and the topic of the most lasting consequence we teach this semester, especially for students who might major in physics. It is the one single topic you will see in this class, in Physics 4B, where the coverage of electromagnetism ends with the derivation of the wave equation for electric and magnetic fields, and in Physics 4C, where understanding of wave phenomena are important for both optics and quantum mechanics, and some of the special relativistic effects. While you will need to wait for the future physics classes to learn about these interesting details about waves, in this class, we will introduce the tools and ways to think about waves that will be useful throughout your physics and engineering education. So, we start with an introduction to waves, kept as general as possible, as the wave description can go much beyond physical phenomena governed by physical laws. Mathematically, the key point in describing a wave is the wave equation, a partial differential equation of position and time. We introduce a version of the wave equation in this class that applies to many linear phenomena. In Physics 4C, you will learn about the Schrödinger equation, the key wave equation in non-relativistic quantum mechanics. Then we will get a bit more specific and talk about the periodic traveling wave, both to connect the wave phenomenon to the simple harmonic oscillators we covered earlier, and as a later building block to wave interference phenomena. In the last couple of segments of this lecture, we covered the derivation of wave speed for the wave on a string, which also serves as an illustration of how we obtain the wave equation from the laws of physics. And we cover some wave terminologies that we will use throughout this week. Please look to the next lecture for the illustrations and discussion of wave interference phenomena, in particular how the standing wave is made up of counter-propagating periodic traveling waves. Of all the things I teach in this class, if I could pick out one thing that would matter when you are doing your career as a scientist or engineer, the one topic that will come up again and again is what we are going to call waves. So let me try to spend a little bit of time trying to introduce this topic, because one of the reasons it's such an important topic is that you see it everywhere. You see it happen. You see the mathematics that we are going to describe now being applied to many different circumstances, some that you cannot even imagine right now. So I want to introduce wave as a general concept. I'll be using some physical demos so that it's not entirely abstract, but I want to keep our discussion as general as possible. So what is a wave? Like, what would you call a wave? I mean, how many here have heard the phrase wave before? Like, it's an existing English word, right? It has some meaning that you associate with it. So let's say, what are some examples of waves that you know? Sound wave, okay. Can you visualize sound wave? No. Not really, okay. So it's not a very good example. Although you have a lab next week, Tuesday, that will actually deal with the sound waves. But so sound wave, it's an example of wave, but it's not a good one that you can visualize. Any other? Like, when someone says the word wave, what do you imagine? What do you visualize? Microwave, can you visualize microwave? Exact same problem, okay. Maggie, what were you saying? Electrical wave? Electromagnetic waves? Yeah, so that's microwave is an example of electromagnetic wave. Electromagnetic wave has the same problem that you cannot easily visualize it. Water waves is one. Like, you see waves on water, there it is. I actually have a water wave demo that I'll bring out for class Tuesday. It's for something else. Any other waves? How about something that's not quite physical? Like, all the examples that you have given me are actual physical waves. Sound wave is one, electromagnetic wave is another, water wave is another physical wave. Yes?
Sine wave, I guess, people do say that. So I guess, I don't know what this will give me if I say sine wave. So, well, it's such a tiny thing. All right, let me just do a plot. So, I mean, yeah, people do say sine wave, and that's because when you plot sine over x, it looks wavy, and that's the shape you associate with the waves. All right, so that's more of a mathematical wave, right? It's something that you can plot that looks like what you associate with a wave. I'm looking for, I guess, something that's non-mathematical, where your intuition, huh? Earthquake wave, that's an example wave, but I think that's another example of physical wave. So what earthquake wave is, you know, if one part of something shakes, like by this, then if you know, put some very precise measurement here, you'll see this portion of the table shaking as well. That's what earthquake wave is. All right. So all the examples that you have given me are examples of waves in science and math. I want you to think about in your daily life, when you're not doing any kind of math at all, no kind of science, if you've ever seen someone refer to a wave.
Like hello, a greeting.
Waving? Yeah, okay, that's a kind of wave. All right, any other waves? Wind? Oh, you mean when the tree branches wave like I'm waving due to wind? Yeah, you know, these two particular examples, they are not actually what we are going to refer to as wave. So, okay, I'll give you the two examples that I like best. One is the waves in a stadium. If you are watching sports events in a stadium, have you seen people do waves? Right? People do this, right? And you know, you see person on your left going like this, you rise up and do the same thing, and the person on your right does that. That's actually an example of wave. In fact, in the sense that we are going to describe wave. It's not physical in the sense that there's no law of physics that tells you how the wave moves across the stadium. But it's an example of wave. You can use a similar mathematical description as what we are using, except you probably have to bring in psychology and human anatomy somehow. Another example of wave, and this is the one that I like the best, and I want you to, I don't know, look it up on your own, is something called a traffic wave. It's, let's see. There's a good Wikipedia article. It's a way of describing motion in traffic, motion of cars in traffic, in a way that's very similar to, let's say, describing sound waves. So I guess this is the idea behind the traffic wave. So, you know, if you drive, you might have seen this, where you are driving along the freeway and the cars comes to really slow down, so you have to come to almost complete stop. And then, you know, they start moving again, so you move again, and you wonder, okay, what was causing me to slow down and stop? And as you drive, you never see anything that actually caused it, right? So traffic wave is something that can explain an experience like that, where, so imagine a bunch of cars, as they are moving, one car slows down for no reason. Maybe for no real reason. So when this car slows down, then this distance gets shorter, so this car has to slow down also. And by the time this car slows down, this car speeds up again and moves off. But the car behind this car also has to slow down also, because the distance is decreasing, and then this goes on. And the car behind it has to slow down, car behind it has to slow down. So this sort of a narrow gap that happened once, it sort of moves backward in traffic from interaction between cars. And so that's one more thing that you can describe as wave. Oh, in fact, I have a demo that can be kind of used to illustrate something like this. This is a slinky. Imagine the rings of this slinky are like the cars. Then what you have is you have something that causes a compression here. And that compression travels along the slinky. Okay? So, you know, for this class, we are obviously going to focus more on the physical waves. But I want you to get used to thinking of waves as a general term for describing any phenomenon that looks like what we are describing. So let me give you a model of wave that we are going to use throughout this class. Well, throughout the remainder of this class dealing with the waves, which is today and next week. So the easiest model of wave is wave on a string. So that's what we are going to use the most. So imagine something that's stretched over a space. So something stretched over a space. And what we call wave is what you see when I move one end. So when I shake one end up and down, you see something moving across. You see something moving across, right? Yeah, so that's what we are calling wave. So when you look at a wave, what does it involve? Would you say it involves motion? Okay. Would you say it involves movement? In this case, horizontal movement. Yeah, this is one where you have to be careful. I see Steven shaking no. It's because, I mean, when you look at it just simply, it does look like something is moving across, right? Like, you know, I shake this end, and at some time later, that other end shakes. So there's some quantity that's moving across, but if you ask the question, is it a spring that's moving across? The answer is no. I can actually mark a section of the spring and see how it moves. So let me just, I don't want to affect too many things. Let me just look at this blue tape marked section. If you can see it, I don't know, it kind of blends in. So when I shake one end, oops, yeah, you can't really see it, right? Yeah, this is why I'm going to do the simulation. So you see me shake, so you have a image of the physical thing that's the wave. But let me do the rest of the discussion in the simulation. It's easier for you to see. It's easier for me to speak and control the simulation at the same time. So since it's a simulation, let me use this end that actually makes things easier. So what you see as a wave is what you saw. This is kind of simulation of what you saw before. I move this end, and that movement sort of propagates through. In fact, let me change it to this. It's a little bit easier that way. I press a button, there's a pulse that goes through. Yeah? Now, it does look like here, something is moving across from left to right, right? But if you ask the question, are any of these beads moving from left to right? The answer is no. So let me do slow motion. Start up, pause, pause. Look at this green bead. See how it moves. As this wave moves across this green bead, it moves upward and then down, and never once it moves left to right. So this is one interesting feature of wave, that when you see wave propagation, by the propagation is the word we use with wave motion. Because we do want to separate this kind of motion from all the other motion that we have been describing, where physical object actually moves from one position to another. I mean, so there is a motion here. There's actual motion of mass here, but that motion is up and down. The wave propagation is from left to right. So, so something is moving across. What would you say is moving across in this motion? Oops. Let me just keep to simulation. So as I do the simulation, you'll have to imagine me shaking the string. So, I mean, so something is here moving across this string. So we want to identify some physical quantity that we can say, well, okay, so no, there might not be any mass. Might not be any mass that's moving across, but we want to say this physical quantity is moving across in the form of wave. Yeah, energy. Yeah. So, I mean, you see it here. So right now, this is the whole system with zero energy or at the lowest energy. This pulse, what it does is it puts in a little bit of kinetic energy on this side. Actually, kinetic plus potential. But so right now, as the way things are set up, you have a lot of energy here and no energy here. And at some later point in time, that it moves across so that now it's this end that has more energy. these beads are moving up and down, so there's kinetic energy. And when it's stretching the string, there's a potential energy there. So this end has a lot of energy. Energy that started out here has moved across to that end. Yeah. In fact, this simulation has a little bit of damping built in. That's why you see the pulse getting smaller. If you get rid of damping, so no friction, then this energy moves across without changing. Good? So that's a wave. That's what we describe as a wave. Let me give you two different descriptions. So what we just described now is, I guess, so what is wave? We could describe it as, I guess it's better to say this is what happens in a wave. What happens in a wave is that energy moves across space without movement of mass. But I'm hesitant to call this a definition, because when I call something definition, I feel like there should not be any counterexamples. And I think I put in this without movement of mass to try to rule out some counterexamples. Because you could say, if I simply say energy is movement of energy across the space, if I throw this mass across the space, like that doesn't look like a wave, but that would fit this definition. So I say without movement of mass, then that gets a little bit closer. But I just want to say this is more of an intuitive description. And one other intuitive description that you will hear from time to time is that wave is oscillation. That's actually why we did oscillation before. Oscillation in space and time. So you have seen oscillation in time, right? So oscillation in time is this. I put this mass on a spring. Over time, it oscillates up and down. So one way you could actually describe wave is, imagine this is oscillating up and down, but as it's oscillating up and down, somebody moves it across at a constant speed. Then the position of this will track like that sine wave. So, this has some validity, but once again, I don't want to really use that as definition, because in fact, the description of wave is more general than oscillation. Oscillation covers a very particular type of wave that we'll talk about. So let me just put quotation marks around this. And really, I think the best way I can describe wave in a way that you don't have to correct anything in the future when you have taken more physics and math classes is to describe it mathematically. I can describe wave mathematically, so let me do that. So by the way, waves are the one topic that you will see across, if you take 3 semesters of calculus-based engineering physics, wave is the only topic you will see across all those 3 classes. You are seeing it in this class right now. And in physics 4B, if you take it with the correct people, you will see derivation of electromagnetic waves towards the end of the semester. And in physics 4C is when you are going to deal with optical electromagnetic waves, optics, and you are going to talk about deal with the quantum mechanics. And one of the ways of describing quantum mechanics is through analysis of wave. It can be called wave mechanics. There are other ways of approaching quantum mechanics. So this is what I mean. Waves are the most important topic that I can teach you. Because you are going to see it in many different contexts. So let me do this description of wave, this mathematical description of wave. So you've seen here that wave can take many different forms. Oh, by the way, so this would be one form where you get sine wave, what you thought a wave should look like. And another way I can do wave is actually this. And I can move this kind of however I want. It's up to me. And this shape that's moving across, that describes wave. So the complicated shape you saw, not a pulse, not a periodic thing, but something that's essentially whatever it was I wanted to do, we want to have a description wave that's so general that it can describe that. So we are not going to be able to describe with a function like, if we try to say waves are something that takes a form like this, well, that's not going to work. It's going to work for some waves, but not all waves. So the equation that I'll need to write down is actually not this equation. Equation that I'll need to write down is actually, it's similar in form to the other equation that you have seen. When we were covering oscillations, you saw equation of motion, which said the double time derivative of something is equal to minus some constant that I'm going to write it down as omega squared times the constant. Like this is what you saw, right? So with the waves, what I can do is I can write down the equation of motion for a wave. So I'm approaching this from entirely different direction from how we did the oscillation. With the oscillation, we started off with the physical system, and we derived this. But because wave is so general, what I want to do is, instead of starting out with the physical system, I'm going to give you the end point. So let me write down the equation of motion for something that we can call wave. Or there's the whole equation of motion for a wave. It's a very long phrase. No one ever really says that. We call this the wave equation. So let me write. So the proper way to call it is the wave equation. Let me see if I have it memorized correctly, because I'm going to have to try to write it down from memory. So it's just like this equation of motion, it's going to be a differential equation. So it's going to involve derivatives. Let's say it's an equation of motion for some kind of function f. Some kind of function f. This f is going to be a bit peculiar. It's going to be a function of position and time. That kind of makes sense, right? So this is what I want you to imagine. When you look at these waves, when I try to describe this wave, I need to describe it with a function of position and time. Think a function of position is easier to see. Right now, I have frozen the time. So right now, what you are seeing is not a function of time. It's a snapshot at a moment in time. And what you are seeing, these beads, you can see different heights of beads, right? These different heights of beads are the function of position. So I could describe this as, I could describe this shape as some height of bead as a function of position. But that's not enough, because right now I have gotten rid of time by freezing the time. But, well, it's also a function of time. It can change as time changes. So this height of the bead is going to be a function of position and time. So it's a little bit easier. If I put it to oscillate, then what you're seeing here, the height of the bead, it can be described as a function of position, as in first bead, the second bead, third bead, the third, fourth bead, and so on. They have different heights. But given one bead, it's going to have different position at different times. So function of position and time. So that's the function that we are trying to specify with this wave equation. So I have this function as a function of position and time. It's a differential equation, so it's going to be described in terms of derivatives. How many here have seen partial derivatives? Like seen this symbol, this weird looking delta, like something like this. Many people probably haven't seen it. You get this in Math 3C. So one thing that I'll tell you so partial derivative is actually simpler than the derivative you know. In your calculus class so far, you only dealt with the function of a single variable, right? That's why you only dealt with the derivative. When you have a function of multiple variables, what we mean by this partial derivative is that when we are taking the derivative, it's something that you already know. When you are taking the derivative, we are going to pretend that t is a constant. That's what we mean by partial. So partial derivatives, when you're taking the derivative, it's actually pretty simple. because it's you take the derivative with respect to x, and you treat everything else like a constant. Yep. So that's one thing that I kind of had to describe, and it's going to be the second order partial derivative with respect to x. So it's an equation. So this has to equal something. And what that something is equal to is, let me work at the, yeah. So it's equal to, it's actually equal to another derivative. It's equal to the double derivative of the same function, f. So you don't have the function by itself anywhere. Double derivative time. And then it's going to need a constant, because each time you take the derivative, this actually reminds you of a unit. This gives you the unit of position, right? So it's whatever unit the function is in divided by meter squared. This is whatever unit the function is in divided by second squared. So you can't say these two are equal to each other. There has to be constant between them. And the constant, let me write them as 1 over capital C squared. What unit does that C have? Meter per second, yeah. So it has a unit of velocity. So let me just write it down as a v squared. And let's see in what sense this is a velocity of whatever. Okay. So this is what we call wave equation. And I guess, so I was hesitant to define what a wave was. We could say, well, wave is a function that satisfies this equation. By the way, this is not the only wave equation, but this is one of the wave equations. In quantum mechanics, the wave equation actually looks a little bit different. But this is the classical wave equation. So if you have something that you can describe as wave, then you have to be able to describe in a way that the function, it can be a function that describes, in this case, it's a function that describes the height of the beat. In terms of sound wave, it would be a function that describes the pressure at a given point. Electromagnetic wave, it's a function that describes electric field and magnetic field. What other example of wave have you given me? Oh, water waves. That would be the height of the water surface. Any other waves? Yeah, so you have some parameter, and when you have a mathematical description for that parameter, it's going to satisfy this equation. So that's what we are going to call wave. Okay, so what I want to spend a little bit, but not too much time, is writing down form of a general solution to this equation. I can actually write down a form that every solution to this wave equation has to satisfy. As in, so we have, we can always simply write down, I have a function. I have a function g of position and time, right? You're just imagining of some function of position and time, like that doesn't do anything. What I'm saying is that once I start requiring that this is a function of, this is a solution to this differential equation, then I can constrain this function to take a very particular form. As in, if I say g is as an independent function of x and t, I can say, well, I can actually rewrite this as another function of a single variable, as long as this single variable is formed in a very particular way out of this x and t. Let me give you some intuition for this, actually. You can intuitively get at this. Let's see, pulse. Yeah, slow motion. Let me generate a pulse. Okay, there you go. Let's just say that I have a function, h as a function of position x, that describes this shape. If you plotted this h of x, if you plotted this h of x on a plot, as a function of x and h of x, then its plot would look exactly like this. Like you can imagine that, right? Oh, and I guess what I'm asking is, what would you need to do to this function so that it's not just a function of position, but it'll be a function of time also. And when you let time flow, that this function, new function of position and time, will describe this wavy thing that's moving across. Like, have you learned linear transformations in your math class that describes how you would modify a function to describe a shape that's moving, that's translating? Really? You covered this in algebra. As in, you have this function parabola. You start out with this, let's start out with the function, You have, this is y is equal to x squared. And instead of describing this, you want to describe this new function. This parabola moved a little bit over, like this. What would this be equal to? Like, how would you describe this new function, which is the old function simply moved to the right? One person at a time. Arjun.
1 plus x squared plus some constant plus...
You add something, but you have to do it carefully. Someone here who knows how to translate a function. Yeah, so you change the x, right? So you are going to take this x, and so you say the plus, but when you do it, you will see that it doesn't quite work. It's minus, right? Yeah, x minus whatever distance d that you are moving it across, squared. This is how you translate a function. I'm pretty sure this gets covered in algebra. Yeah, so if you have forgotten it, then that's the sense that I want to remind you of. So when you look at this function, so all we are seeing here is that as a function of time, it's getting translated across the space. So because I'm a little bit out of time, let me just give you the answer. So, so this form of function that this will take is that you start out with the actual original shape. So you might say h as a function of this, x. And what you need to say is that now you need to have a term that describes how this shape is translating across the space. And for that, I write down velocity times this v times this t. Does that make sense? Like, does this make sense that if I told you that if there's a function that I can write in this form, that I can write down as a function of a single parameter where position and time are combined in this very specific way, then this will result in a motion that looks like what you're seeing here, a stable shape moving across the space. And this would also correspond to satisfying this wave equation. Does that make intuitive sense? If it does, great. And especially if it doesn't, doing the math, that's actually the easier portion. So let me prove that if I have a function in this form, this actually does satisfy this wave equation. Because I think it's a lot easier to demonstrate that. So let me do that. So let's say I have a function, f. And instead of writing it as independent variables x and t, I'll say this f is a function of x minus vt. So it can be, many different examples I can give. It could look something like, so if you're trying to think of examples, this can be something like some amplitude times exponential of minus x minus vt squared over some characteristic length lambda. This is something that you can actually plot on Wolfram alpha, and you'll see a little bump that moves across. So something like that, but some complicated function that could look like this, where the only constraint is that wherever you have the variable has to be organized together in this way. Okay? Let me prove that this satisfies wave equation. So how do you show that a function satisfies a differential equation? You take the a derivatives. So I'm essentially just plugging this into the equation to see if this equality holds. So yeah, that's all I'm doing. So when I do that, so I'm going to need to take some derivative. So let me do that. So I need to evaluate the partial derivative of f with respect to x. This is where I will need to use a chain rule. So I take the derivative of the outside. That's going to be something, I don't know what. Let me just call that f prime. And then I have to take the derivative of the inside. Well, I guess that's just the one. Right? So all right, the one derivative, that's just f prime times 1. But let me just clarify. This would be f prime, function of a single variable, where the input of that variable is x minus vt times 1. Yep. Okay, I need a second derivative, so let me take one more derivative. So if I take one more derivative with respect to x, then so it's going to be f double derivative, f double prime, and that's some functional form. That's some kind of form. If you take this example, imagine taking it's exponential of minus g squared over lambda. And imagine taking derivative with respect to g twice. That's what you get with the f double prime. So it's some function. I don't know what exactly. But it's going to be a function of x minus vt times derivative of the inside is once again 1. Good? So this is the left-hand side of the wave equation. Let me calculate the quantities I need for the right-hand side. I need a double time derivative, not the position derivative. So let me take the derivative of f with respect to time. Then the derivative of the outside will be the same because it's the same outside function, f prime x minus vt. Now this is where I have to be careful. Derivative of the inside, so I get a factor of minus v out. Right? So times minus v. I need the second derivative, so let me take one more derivative with respect to time. So for this outside function, I get f double prime, function of x minus vt, times another factor of minus v. So it will be now minus v squared. Good. Let me plug both of these into the form, into the wave equation. So I get f double prime x minus vt, is it equal to 1 over v squared times f double prime x minus vt times minus v squared or v squared. So you see that v squared cancels out. And this is really the step that proves that this coefficient that we have to put in here, that is the velocity. That if you are correct to say that this is 1 over velocity squared. Because when we have a form of the function where meaning of this velocity is much clearer, we get that in the process of proving that it's a solution, that yes, that cancels out. That's the only way they can combine. And the remaining is this is equal to that. Yeah, it's the same function over again. So A is equal to A. Okay. So this is a general form of a solution to the wave equation. I should say this is the general. I should put a little qualifier, traveling solution to the wave equation. All right. I think that's good enough. Okay, so all this is sort of going off to that and then not doing anything. So what you are seeing here, so this is traveling wave. Everything here is traveling from left to right, and it's periodic because the source is rotating at a constant rate. So it's shaking this at a constant rate up and down, up and down. You could another thing you could also imagine happening physically is if you imagine that this end is attached to a kind of a mess on a spring, and imagine that this mess on a spring, Yeah, those speeds 없네. But imagine this mass on a spring is oscillating up and down at the natural oscillation frequency. That's how you do get something that looks like a periodic traveling wave. So what I would like to be able to do is write down a mathematical expression for this traveling periodic wave. And I'm going to be using that mathematical expression to show you a couple interesting features of waves that's not trivial to get at, and it's interesting. So this is the first question I want to address. What kind of mathematical expression will describe this traveling wave? Yes? So it has a sine shape, right? So we can use that at least as a starting point. So one thing that we can say is, well, let's say this is the wave at time equals 0. Then we can say this. At time equals 0, this is what the wave looks like. It goes on forever. So we can say, all right, this height, the height of the bead as a function of the position of the bead, x, at time equals 0 is something that's described by sine of x. When we did the waves, do you remember what we, so I think we did this when we went through wave. Like what I wrote down here, it's not quite correct. There are two things wrong with it. Do people remember that from waves? Yes. What am I mainly looking for when I'm trying to figure out what's wrong with this expression? Yeah, units is the biggest thing. So because in order to make the units come out right, I need to have a constant here so that the argument to sine is unitless. And I need to have another constant here so that the unit on the right-hand side matches this unit here. And let me give you this constant in the standard form that you are going to see it. It's this constant here is k. And we have a name for this constant. Let me write it down under the list of terminology that you should know. So that k there is referred to as wave number. Don't ask me why it's called wave number. That's just the name for it. And that's what's represented by that constant k over there. And it's going to be related to something else that we are going to define in a little bit, something called wavelength. So wave number and wavelength are related to each other, and we'll talk about this in a little bit. And we need one more constant here. That's the amplitude that we have already been talking about. So this function will work for describing wave at time equals 0. It works for a snapshot picture. But we need to be able to describe the wave as a function of time as well. So using this as a starting point, how should we modify it? So that we have a function as a function of time that will describe the movement of this wave for all time. Like if I let time flow, what happens to this shape of wave? Like what kind of mathematical transformation would you describe this with? Stephen? It's moving. There's a particular term that you have seen in either geometry or algebra. Remember, we are dealing with a function, and we are trying to describe a transformation that's happening to a function. A velocity is not a transformation, right? Sorry, what? Change of an angle. I think we are trying to describe change in phase. So that might work if you're trying to pick a single point and look at that. But I want to connect it to something that we were doing last time, something that we were doing last Thursday. Yes, Asia? Yeah, linear translation. You have this shape or plot of something, and over some time, this is moving across. We call that translation, or linear translation. So this is one way we can get at what this time should be. This function of position and time, it's something that's going to describe this shape that's being translated across space over time. So what we need to have here, so the way I should modify what's written here is where I see x, I should replace this with x minus vt. That's what you do for translation, right? Yes? And this is what we did the last time too. So in fact, what you see here, so now it's a function of time, not at time equals 0. So this is exactly in the form that we are describing before as the general solution to the wave equation. In this case, we are giving the form of this function g, that it's sine. Okay? Or it could have also been cosine. Okay? So let me write that down, and let me express that function in a couple different ways. That'll be a way to introduce all the terms you are supposed to know about a traveling periodic wave. So, so the mathematical description of a wave, we can describe something that looks like this. Function f as a function of position and time is equal to amplitude, let me use my standard symbol, amplitude times the functional form, sine, and the argument to this has this constant k times x minus vt. Okay. That's actually not the most common way we write it. I mean, this is correct, nothing's wrong about this, but there's the more common way we write it. So let me rewrite it in that way, and that'll be a way to reintroduce a term that you already know, kinda. So I can write it this way. I can expand this out. Then it'll be a times sine of kx, and then k minus kvt, minus k times v times t. And I guess I want you to have some kind of an intuitive guess for what this coefficient should be. It's something that you have already seen. Anybody recognize it? It's a little bit far removed, so it might not be as easy to remember it. So this is the picture that I like to imagine when I'm trying to think about it. So far we've been trying to describe the function, the wave, as a function of position, right? You know, whenever I needed to draw something, I stop the time. So I've been taking snapshot. The snapshot description is one way to describe wave. Another way to describe wave is you fix the position. So instead of saying I'm going to look at all the different positions of wave at a single moment in time, I'm going to do the exact opposite. I'm going to look at a single position of the wave, single x value, and look at that over different values of time t. So let the time go. Then this is what I'm trying to describe here. So I fixated on this green bit that's moving up and down. That's a single position x that I'm looking at. You could say that this is where I said x equals 0. And if I'm describing the y position of the speed, what do you think that would look like? So, you know, y at x equals 0, but as a function of time. Roughly speaking, what do you think that should look like? Is that something you have seen before? You have never seen motion like this before? Yeah, mess on the spring, oscillation, right? That's kind of why we do oscillation before waves, because you can actually get to oscillation from wave. So all that oscillation is, you take the wave and you fix the point. So you only look at it as a function of time. That's oscillation. So in a very rough way, I'm ignoring some details. You could say this is some amplitude of the oscillation times the trigonometric function, sine or cosine, sine of, and when we are describing oscillation, there was angular frequency or the natural frequency omega times t. So this is what I want you to remember, that when we are describing something with a very definite period, some kind of regularity, we have a picture of oscillation. So when you come back to this, when we say x is equal to 0, this is the term that remains. And this should be equal to omega times t. So what that means is that this should be equal to omega, angular frequency. So let me write the term here. Angular frequency. So we can talk about angular frequency of a wave, of a periodic wave. And this will be related to at least two more quantities that you have seen. And this is a matter of remembering the definitions and not forgetting them. Angular frequency is related to plane frequency. And what else is angular frequency and frequency related to?
Time.
Time? What kind of time? Describe the time for me. What time are you measuring?
Number of cycle that we did.
Time for one full cycle, right? So here I'll be measuring something like, okay, start, time, end. That's what you would be measuring, right? So we call that period. So the angular frequency and frequency will be related to period. So recognizing, I'll just use capital P. Recognizing all these relationships is important because a given problem may give you information for these in terms of only one of them. And my expectation is that you can work out the remaining from remembering relationship between these that we'll write down soon. Yeah? Okay. Let me write down one more thing. So I said this constant k here, that's something called a wave number. And if you're trying to write down a simple looking expression, wave number is actually the most useful quantity to work with. But it's not the most intuitive quantity. For one, any guesses what the unit of k is? What should be unit of k? Could you say louder? I think you are thinking of the spring constant k. So at some point in physics and engineering, you will see a single letter used in different ways. So this has nothing to do with the spring. It's a wave number k, not the spring constant k. So look at the equation itself here. What unit should this k have so that the unit for everything works out correctly? Isha? Yeah, 1 over meter. That was the entire reason behind introducing this k here. So that times something that's in meters will give me something unitless. So this k must be 1 over meter. Okay? So wave number is a quantity that has unit of inverse meter. Do you know anything that has unit of inverse meter? I don't. There's nothing that I know that has a unit of 1 over meter. So that makes a wave number difficult to relate to in an intuitive sense, at least at this level. When you do quantum mechanics, actually you can, but we are not doing quantum mechanics. So that's why I want to relate this wave number k to wavelength, which will be in unit of meters. So it'll be easier to intuitively relate to the quantity wavelength. So let's just work out the relationship between wave number and wavelength. I'm gonna take a snapshot again. Okay. So let's say we are trying to describe this wave in the snapshot view again. I'm looking at this wave at time equals 0. So I am looking at these different positions of the bead. I don't think we've explicitly talked about the quantity that we call wavelength. But what does wavelength sound like? Like length of wave, right? And you know, if you're talking about the length of this string, that's infinite. It has no end. So that's not what we mean. What we are talking about when we say wavelength, it's the spatial version of a period. It's how long of a distance do you need to go before the wave starts repeating itself again. So wavelength is something that's meaningful only for periodic wave. Because if it's not periodic, then it won't repeat itself. But if it is periodic, at some point it's going to start repeating itself. So here, what we would describe as wavelength is from this point to here. That's wavelength. So, and there are actually a few different ways of measuring wavelength. Let me just diagram 3 different ways of measuring wavelength here. You could do it the way I was just motioning. Start from here, 0, and end here, because that feels like one full wave. So you could say this is wavelength. And there's a symbol that we use, a standard symbol for wavelength. It's this symbol. How many have seen this symbol before? Yeah, Greek letter lambda. It's lowercase lambda. That's the standard symbol for wavelength. Yeah, well, I think I mean, like other symbols, sometimes we use this lambda for other quantities, but in the context of wave, it stands for wavelength. So this is one way to measure it, but actually this way is somewhat prone to mistakes, because sometimes people see another 0 here and think that that's where your wavelength is. And it's not, because after that 0, it's not repeating the same thing over, it's upside down. So if you don't want to make the mistake, one way you can measure wavelength is you can do it peak, what's called peak to peak. So this is a peak. It's the highest point on the wave. And you can keep going until you see another highest point on the wave. So this would be another way to measure wavelength, lambda. Or one last way to measure wavelength, lambda, would be what's called trough to trough, the lowest point to the lowest point. So from here to here. And I want you to see these drawings and convince yourself that these 3 different ways of measuring wavelength gives you the same number. So however you are measuring it, it gives you the same wavelength. Okay. All right, so that's the quantity wavelength. So I guess what I want to do is I want to figure out the relationship between k and lambda. So let me get the correct color of the pen. So actually, I haven't used the green yet. Looking at this, and let's say I want to express k as a function of lambda. How would k be related in terms of lambda? In other words, if I wanted to rewrite this in terms of lambda, what would it look like? So let me just do the easy part. Based on the unit, you might say it's 1 over lambda. And if you did that, unit will be correct, but it won't be quite correct. You'll be missing something. So here's one way to think about it. So let's say this position is x equal to 0, right? And this position then will be x equals lambda, right? Let's say we are looking at the description of wave as a function of position alone. Y of x, time equals 0, is 8 times sine of kx. So you know how x changes from here to here? Do you know how the value of kx changes as you go from here to here? So here, let's say kx is 0. It really can't be anything else. What is kx equal to when you are here? When you have gone 1 full cycle. Not 0. I mean, okay, you are wrapping it around. I don't want you to take modulo of whatever you are doing. Because it's at different point. If I say kx is equal to 0, that gives me a nonsense answer for x. I don't want that. I want a reasonable answer for x. Asia? 2 pi, right? So one cycle is 2 pi. So at this point, what we can say is kx must be equal to 2 pi. Now we have enough information to solve what k should be. X is equal to lambda, so k is equal to 2 pi over lambda. So that's the relationship between wave number and wavelength. Wave number is related to wavelength by 2 pi over lambda. And in fact, that gives you another way to write down this form of wave. That would be something like this. Amplitude times sine of, and instead of writing in terms of k, we do it in terms of wavelength, which is easier to relate to intuitively. So we say it's 2 pi over lambda times x. And then I guess I can keep this minus omega t. Good? All right, let's go over the relationship between these three. I think that you have seen it before, so I'll write it down. Hopefully it looks familiar when I have finished writing down, and we won't need to discuss it. But if you have questions, let me know. So this is the memorized relationship between all these three. Omega is related to the frequency this way. Angular frequency omega is equal to 2 pi times frequency f. The way I remember it is f is given in cycles per second. I want omega in radians per second. One cycle is 2 pi radians. That's why there's this 2 pi there. Good? And period, it's most directly related to the frequency. Period is equal to 1 over frequency. So if I want to relate period all the way to angular frequency, that would be, so f is equal to omega over 2 pi. So it'll be 2 pi over omega. Or another way to say is omega is equal to 2 pi over period. Okay. And by the way, this expression is kind of a justification for what I was saying, that wavelength is the spatial version of period. The relationship is the same. But let me not dwell on it. So let me actually plug this in to rewrite this in terms of, I guess the most natural one to write it in is actually frequency. Then this is another way I could write down the mathematical representation of this wave as amplitude times sine of 2 pi over lambda x minus, rewrite omega in terms of frequency, 2 pi times frequency times time. Okay? Just as a reminder, the only variables here are the ones that I'm going to rewrite in purple, x and t. Those are the only variables here. The rest are supposed to be constant. And so, this is another way you could write down the mathematical representation of your wave. And so this form is really why this is the preferred form. And this is really why we introduce wave number. When you try to describe a wave mathematically in terms of wavelength, just because of the way sine is defined, you'll get a bunch of factors of 2 pi. And you could say this, the reason we introduce wave number k is so that we don't have to write down all those 2 pi's. So 2 pi is included into k. It's here. We remember that that's there. But when we are writing down, we just have to write down k, not 2 pi over lambda. And we just have to write down omega, not 2 pi times frequency or not 2 pi over period. But so this is what I'll tell you. You should be familiar with all these different relationships, so that if a question asks you to write down a mathematical representation of wave, write down a mathematical representation of wave into something that looks like this, and if it somehow gives you the period and wavelength, you should be able to figure out what is my wave number and what is my angular frequency. Good? Okay, so before we go into break, let me go over just one more idea that relates to these parameters. So what you're going to find is that wave velocity is a special quantity. So let me ask you this question. What things can you do that will cause this wave to move across the screen faster? So let me actually do that with a physical example first. So if I have this slinky, and you have a sense of wave speed. Like I move one end, and it takes some amount of time to get to that end, right? Let's just say this is about a meter, and 1,001, 1,002, about 0.5 meters per second. Right? That's the wave speed right now, right? Now, this is my question. What can I do to change the wave speed so that it moves across faster? Will it move across faster if I put a greater amount of energy? If I make the amplitude bigger, will it move across faster? Yeah, you just saw that it didn't really move across any faster, right? Let me do it again. So small amplitude, 1,001, 1,002. Big amplitude, 1,001, 1,002. About the same amount of time. Maybe it's not the amount of energy. Maybe I should shake faster, higher frequency. Let's see if that changes it. 1,001. I'm not a good drummer. So this is what I should do on this end. And let me do that and then count 1,001, 1,002. 1,001, 1,002. So whether I do this shaking gradually, 1,001, 1,002, or whether I do the shaking really quickly, the amount of time it takes to travel across doesn't change. So what you're finding with this example is that wave velocity, it's a constant. It's the property of the medium. Yes? Yeah. So I want you to mention that now before I write down the next expression that's going to come out of this expression that we wrote down earlier. This expression here that we wrote down earlier, it can be actually used to write down one of the most important expression in dealing with the periodic waves. Let me write it down in equation form here. kV is equal to omega. So let me solve it for V, wave speed, wave velocity. V is equal to omega over K. Let me do a little bit of algebra and actually rewrite this in terms of something that that's more intuitively relatable. That would be for omega, it would be the frequency is more intuitively relatable. There's a whole unit of frequency, hertz. I don't know if I mentioned it. And K, we will rewrite it in terms of lambda, wavelength. So when I do that, omega is equal to 2 pi times frequency. K is equal to 2 pi over lambda. So these 2 pi's cancel out. That's nice. I kind of don't want to be writing 2 pi's all the time. And so 1 over lambda, goes back on the numerator. So we get wave speed V is equal to frequency times the wavelength lambda. This is one of the most important relationships. But as you learn this relationship, what you have to know and memorize and internalize is that the fact this wave velocity V is property of medium. Property of medium. Another way to say it is in most cases, this V is a constant. So that actually has an implication. So let me illustrate that implication on this simulation here. So you have seen how fast the wave moves across, right? And what you have seen with this illustration here is that when you increase the frequency, the wave velocity V doesn't increase. But because this expression relates to three variables together. If one changes, if frequency changes, something must change. The intuitive thing might have been to say the velocity increases, but you have seen this in this physical example that doesn't happen. So what must change if a frequency increases, for example? Lambda, the wavelength, the only last remaining quantity, this must change. And that's what you can see with the simulation. I can actually change the frequency here. Let me double the frequency. What do you think will happen with the wavelength? Decrease down to how much? Half, right? Okay, let's try that. Double the frequency, 3 hertz. And yeah, wavelength decreases down to half. So this is one of the important properties of a periodic wave. So before we go into break, let me just tell you this. This is what you must do if you want to change the velocity of the wave velocity. You have to change the medium itself. So how you change the medium, it kind of depends on what the medium is. The sound waves that you will deal with in the lab today, the way you can change the medium, you can change the temperature and the pressure. With this slinky, one way I can change it is, or two ways I can change it. I can change tension, and I can change the linear mass density of this. So if I pull this, I have increased the tension, and I have also made it less dense. You will see that the wave now travels faster. Right? Same distance, but 1001 travels faster. So, or in this simulation, this is what I can do. I can keep the frequency the same, but by decreasing tension, I can decrease the wave speed. Then what you see is that even with the same frequency, wavelength decreases because so wavelength decreases if wave speed decreases. Okay? So for today, it looks like I don't have time to actually derive it, but let me write this down as a formula that I really think you should memorize. I will derive this maybe next Tuesday. So there's a formula that you can look up in your textbook. That's the speed of wave on a string. And this is a formula that's relevant only for this case. That speed is given by square root of tension divided by linear mass density, meaning however much there is divided by the length of the string. Okay? So this is a formula that, let me try to derive it next Tuesday.
Whenever you are dealing with some wave phenomena, your starting place is the wave equation. So let me just copy over here on the screen what I have written down there. Wave equation. It takes this form. This isn't the only wave equation, but it's the one that you will see in this class. It's a second order partial differential equation of a function that's both of position and time. And there's some constant coefficient here, and there's the second order derivative with respect to time. And when we talk about solution, wave functions, we are talking about solutions to this wave equation. And what we don't really talk about in detail in lecture is where does this wave equation come from? It's just plopped from sky, like it's given to you by God. And the true picture isn't like that. The answer to the question, where does the wave equation come from? It comes from physics. And one of the reasons I don't give the explicit description of where the wave equation comes from is it's really situation dependent. So you will see this wave equation derived in physics 4B. If you take physics 4B with me, then the very last thing we do at the end of the semester is use something called the Maxwell's equations that describes electromagnetism and derive a wave equation for electromagnetic waves. And so it comes from physics. That's one example. And each physical situation you have, how this wave equation comes about, it'll be situation dependent because it's very specific to the physical setup that you are looking at. And I think it's worthwhile to look at least one specific example that we use a lot, that I use a lot, the waves on a string. And your textbook does have a fairly good description of that. And I think what probably the best use of our time here is just reading through the section. I kind of skimmed over it before the session, and I think it's decent. I don't see the point in reinventing the wheel. And this is one of those derivations that's subtle, not complicated. Um, it's involved enough that whenever I cover it, I would need to do some prep myself. So I wouldn't trust myself to just do it from scratch correctly without any prep. And um, if I'm doing it with a textbook section in front of me, I'll be going through most of the same steps that the textbook is. So I think what's good for us to do is just read it through the section together. And maybe for me to clarify some of the things that the textbook is doing, some of the things that they don't fully explain that I can tack on my explanation of. So, yeah, so I guess I should just to read out loud. Yeah, I know everyone knows how to read. This is more for just the pacing of this particular lecture session. It's not that long. It won't take too long for me to read out loud. So this is from section 16.3, wave speed on a stretchless string. The speed of a wave depends on the characteristics of the medium. For example, in the case of a guitar, the strings vibrate to produce the sound. The speed of the waves on the strings and the wavelength determine the frequency of the sound produced. The strings on a guitar have different thickness, but may be made of similar material. They have different linear densities, where the linear density is defined as mass per length. This is going to be one of the parameters you will see in the expression for the wave speed on a string. Mu, the symbol that we use, mu. In case you haven't seen it before, it's spelled out with the Roman alphabet as mu, uh, uh, pronounced like mu, not mu, as I do. Um, it's a mass of the string per length of the string. Depending on the question, they might give you this directly or give you the quantities that you can use to compute it from. Okay. In this chapter, we consider only strings with a constant linear density. If the linear density is constant, then the mass delta m of a small length of string delta m is equal to mu times delta x. For example, if the string has a length of 2 meters and a mass of 0.06 kilogram, then the linear density is, they do some calculation. If a 1.00 millimeter section is cut from the string, the mass of the 1.00 millimeter length is, and some calculation. So when I read through technical text like textbook, I like to skip over these equations like this, at least on the first read. And if I recognize them as being important for the comprehension of the text, then I would go back and read it. But a lot of the times, you can skip the equations and it'll be fine. So that's why I'm saying just skipping it basically. The guitar also has a method to change the tension of the strings. The tension of the strings is adjusted by turning spindles called the tuning pegs around which the strings are wrapped. For the guitar, the linear density of the string and the tension in the string determine the speed of the waves in the string, and the frequency of the sound produced is proportional to the wave speed. And guess in this section they are not making it explicit. There's also standing waves stuff happening. That's chapter 17 material. Um, so wave speed on a string under tension. To see how the speed of a wave on a string depends on the tension and the linear density, consider a pulse centered on a taut string. I think the figure that that's not a, oh, I guess they are describing a taut string. Okay, so let's just look at this figure. This is a taut string, and what's important in the description of this is they are drawing two tension forces that are acting on this segment of the string. That they have to be equally magnitude because this section is accelerating in either direction. along the string. So, so that's what this figure is illustrating. Yeah, it's in static equilibrium. When the top string is at rest at the equilibrium position, the tension in the string Ft is constant. Sure, I guess that's one way to say it. Consider a small element of the string with a mass equal to delta m is equal to mu times delta x. The mass element is at rest and in equilibrium, and the force of tension of either side of the mass element is equal and opposite. Okay. If you pluck a string under tension, transverse waves moves in the positive x direction, as shown in the figure below this figure. And and just because this is a kind of stationary figure, and sometimes with the stationary figures there can be some sources of misunderstanding. Let me just make sure you have the right mental image in mind as you look at that particular figure. This is my favorite simulation on FET simulation website. I think it's called Wave on a String. Yeah. And it's really great for illustrating waves, especially transverse waves, which is the only thing it can illustrate. So, wait. Um, so I guess the easiest thing to do here is for me to show a pulse. So let me just do it as a slow motion so I can um, have time to stop the thing. So when you send down a pulse along the string, then you can imagine this as being a kind of this pulse. So this is a snapshot as a moment in time. And over time, what you have to imagine is, so this, or I guess this mass element here, it's going to be accelerating or moving downward. As you can see here, if I'm looking at this green bit here, over next few moments in time, this green bit is moving down, downward. And so there's a vertical motion up and down. So if you imagine mass elements on this side, as the wave moves across, this mass element moves up, and then it pauses at the top here, and then it moves down. Or if you imagine tracking this green bit, as the wave moves across it, it moves up until it reaches a top point here, and then it moves down. So there's going to be a kind of an oscillatory thing happening with any particular given string element. And that's what you should imagine as we go through this analysis. So we were at, shown in figure. The mass element is small, but is enlarged in the figure to make it visible. It's going to be infinitesimal size in our analysis. The small mass element oscillates perpendicular to the wave motion as a result of the restoring force provided by the string and does not move in the x direction. As you saw in the simulation, this will oscillate up and down, not left and right for transverse wave, which is wave on the string. The tension Ft in the string, which acts in the positive and negative x direction, is approximately constant and is independent of position and time. Yeah, I guess I agree with that. Approximately. You can imagine if you are shaking the string violently, it might not be constant. So you stay away from that. You stay at the small amplitude region. Okay, assume that the inclination of the displaced string with respect to the horizontal, like this dotted line, this inclination is small. So what they are having you do is they are having you make this approximation that the angles theta 1 and theta 2 expressed in radians is much less than 1. They are using the small angle approximation that you have seen elsewhere in the course. And so it's good to keep in mind what this small angle approximation involves. It implies the following things for the common trig functions. For sine of theta, it means it's approximately equal to theta itself, expressed in the radians. And tangent of theta is also approximately equal to theta itself. And this last one is the most important one. That's why I want you to point this out. Because without this understanding, some of what they say in the derivation can get confusing. Most importantly, cosine of theta under the small angle approximation is approximately 1. So for angles small, so what it comes down to is if you imagine a right triangle like this, a small angle, then so as you change the angle, imagine you are keeping the hypotenuse the same. Then in terms of the opposite side, which is related to sine of theta, that's going to change proportional to theta. But the adjacent side, which is related to cosine, this we are going to treat as being constant. That's the details of the assumptions we are making when we are making small angle approximation, as the rest of the discussion in textbook will. So, assume that is small. The net force on the element of the string acting parallel to the string is the sum of the tension in the string and the restoring force. The x component of the force of the tension cancel. So it's this approximation here that allows you to say that your force of tension is approximately in the horizontal direction, or more precisely, what they are illustrating here is the x component of the force of tension. And under this small angle approximation, they can say that this is equal to the force of tension. Because the force of tension is really along the string. It's not that force of tension along the string is where they get this vertical component. This is the y component of the force of the tension, and the expressions they write down saying that the ft on this side is equal to ft on this side, even though their y components will be different, is because of this approximation here. What they are really expressing is that the x component of the force of tension is equal on both sides, because the string, this string element is not accelerating horizontally. So the x components of the force of tension cancel. So the net force is equal to the sum of the y components of the force. The magnitude of the x component of the force is equal to the horizontal force of tension of the string Ft, which is approximately equal to Ft itself, as shown in figure. Is that the same figure? Yeah, it's shown in figure. To obtain the y components of the force, note that tangent theta 1 here is equal to minus f1 over ft. That's the exact expression for tangent. And tangent theta 2 is, if you're drawing a triangle that looks like this is the opposite over the adjacent. Same thing with the opposite over the adjacent. Tangent theta 2 is f2 over ft. And I believe are they keeping things general? Well, so I guess here theta 1, they are letting theta 1 become negative, I think. Tangent theta is equal to the slope of a function at a point, which is equal to the partial derivative of y with respect to x at that point. So this is the equation they are writing down to express that. Therefore, the f1 over ft is equal to the negative slope of the string at x1. F2 over Ft is equal to the slope of the string at x2. And x1 and x2, we are keeping them as two separate locations, here and here, and they're going to address delta x in a bit. The net force on the small mass element can be written as the net force, sum of F1 plus F2, and it looks like they are so to make a sense of this, I think that they are letting the variable f1 itself become negative. So that's why they are just so they are adding this as vector quantities. And I hope all the signs will work out. Yeah, I guess this minus sign here will address that side. Because f1 being downward with this positive slope is handled with this minus sign. Yeah. So ft times, this is coming from f2, dy, the partial derivative y of x at the position x2, plus this term, which is minus partial derivative y with respect to x at position x1. Using Newton's second law, the net force is equal to the mass times the acceleration. The linear density of the string mu is the mass per length of the string, and the mass of the portion of the string is mu times this delta x here, the distance a bit from here to here. And again, they are using this small angle approximation that cosine theta is approximately 1. So you can treat the length along the hypotenuse basically being the same as the length along the adjacent side. Because delta x is really the length along the adjacent side. But under small angle approximation, all this is fine. Yeah. So this is the expression written out, Newton's second law, mass. You have to be careful here. The delta m here is not difference in mass. It's the kind of small amount of mass, what someone might call infinitesimal mass that's associated with delta x, which is actual difference interval. Um, so yeah, the net force is equal to mass times acceleration. And the next step is just writing out what mass, the small amount of mass is, mu times delta x, and the acceleration. So they are looking at acceleration of the segment along the y direction. So they are saying double partial derivative of y with respect to t, time. So, um, so this is their equation of motion that we were writing down when we were doing oscillation. And having written down this equation of motion, they will now introduce a couple additional calculus steps and simplify it until it looks like wave equation, so that we can identify some of the parameters with this speed that we have occurring in our wave equation. So dividing by this number, force and delta x, and um, so when you look at derivation, sometimes you will see this. I say this is a poorly motivated step. What it really means is when and if people ask, why were you dividing by this number? Oftentimes there isn't really a good answer why, just looking at this. Except maybe if you look forward to where you are trying to get to, then it makes sense. So you want to get rid of ft and you want to put delta x on the denominator here. And doing this does that. But this is the kind of the derivation step that you will be seeing as you move into higher levels of math and engineering and science. That's one of the reasons to read the textbooks, because these steps are not always obvious or intuitive. You kind of have to follow along someone who's done these non-obvious steps. Having divided, you end up with this expression here. This is what you have right after the division. Ft is cancelled out. You have delta x on the denominator. On the right hand side, delta x got cancelled out, and you have ft on the denominator. Okay, so they are both in your equation somehow. And they say taking the limit as delta x approaches 0, you are making this string element infinitesimally small. This is the calculus step. This is why it helps to not skip the things in your math class, even the ones that look esoteric and maybe things that you might think, oh, when am I ever gonna use this? Like the definition of derivative in terms of limit, and with all the derivative and integration formulas you have to memorize in calculus, maybe things like this get lower priority, but if you remember definition of derivative, that's when you can recognize expressions like this. You stare at this for a while, you realize that these two are basically the same functional form, evaluated at two different positions, two positions that are relatively close to each other by distance delta x. You are taking difference between them and then dividing by delta x. And you are taking the limit that delta x goes to 0. All of this should remind you of the definition of derivative. So what we are doing with this left-hand side is taking the derivative of this function here, the partial derivative of y with respect to x, first order. So since you're taking another derivative with respect to x, it becomes the second order derivative as you take the limit x, delta x approaches 0. Right-hand side remains the same. And with all those stuff, you end up with this as your final result. This is the equation that we end up at. And I'm just going to use my own version of the wave equation there. When you look at this equation here, and this is our equation of motion for the string element, you see that it has all the parts that we had in the wave equation. We have the second partial derivative with respect to x. We have second partial derivative with respect to time. And really what this comes down to is matching this constant coefficient with this constant coefficient, mu over ft. So we say 1 over speed squared is equal to linear mass density over force of tension. And this leads to a formula that I recommend that you memorize, and I've ever memorized since undergraduate days. The wave speed on a string is given by square root of the tension force divided by linear mass density. Yeah, this is one of those formulas that's relatively easy to memorize, and deriving it from scratch can be a bit of a pain. So those are really the only formulas I recommend to memorize. Ones that are hard to derive and easy to memorize. So solving for V, you get that. So that's the wave speed on a string. And as I was saying, your textbook covers fairly thoroughly, unlike the wave speed of the compression wave that will just give you the formula of. Yeah, and so I recommend reading through it. And if any of the sections were not clear, then this is my attempt at trying to add some additional detail on some of the approximations that they didn't fully spell out. And yeah, some of the waves they just all right, that's interesting. So here they just give you the formula for. So this would speed of the longitudinal wave. That's a sound wave. So this could be describing speed of the sound wave. I think, yeah. Well, we won't go into detail there.
So let's see. I think this is actually a good point to go over some of the wave terms, because I realize there are some terms that I should have introduced that I kind of forgot to last time. So let me actually use this opportunity to introduce some of the wave terms. So let's see. Wave terms. I think there's one term that we did cover last time. And that one term that we did cover last time relates to this constant here. Or if you are looking for it elsewhere in the things we talked about last time, it this constant here. What does this parameter V describe? Velocity of what? Like, the wave traveling, right? So to be more specific, when we talk about velocity, there's actually two different kinds of velocity. There's a velocity of the bead moving up and down, right? And there's velocity of that shape that's moving across. Here, when the context where these V's occur is not the velocity of something that's, it's not velocity of a physical object that's moving. because that velocity in this example is up and down, and that's not the velocity we are interested in. We are interested in the velocity of this shape, which is moving across horizontally. Okay? So we give it a name because it's a very particular type of velocity, and it's in some sense different from velocity of a tennis ball that we have been talking about, right? So we call this wave velocity. And we will have some opportunity to address this in detail, but this is a new-ish concept. It's familiar in the sense that it's a velocity. It's meters per second. It's describing how fast something is moving. What's new here is what is that something. So far, everything, whenever we were talking about how fast something is moving, that something used to be something concrete that we can touch. With the waves, I'm not sure if you can touch waves, because I think we did do this example last time. So if I send 2 waves, so if I have, so instead of having no end, if I have an end here, and if I send 2 waves, and when 2 waves kind of touch each other, they simply move past through each other. They don't really collide, right? We did this last time, right? Yeah, and we'll talk about this in a little more detail. So the wave as a concept is kind of new, because you cannot touch a wave in the same way you can touch physical objects. Yeah? So for the velocity of that wave, we're going to give it a new name, wave velocity. And there are actually a few more terms that you already know that that we didn't explicitly talk about last time. The biggest of that would be, I guess, I could call it amplitude. Or if I want to be explicit, I could call it wave amplitude. Like, what do we ever mean by amplitude if we're talking about amplitude? Like, in what context have you seen that word, amplitude? I mean, you have seen the word amplitude, right? It's not new. So in what context have you seen it? Asia? Yeah, with oscillations, right? That's why I have this pendulum. So amplitude describes how large the oscillation is. Or, in general terms, you can say amplitude refers to sort of the size of the displacement. So here, if we are talking about amplitude, so this would be amplitude. So this, the dotted line is the equilibrium position, and how far away this point is, that's the amplitude. And you can see that there is a relationship between energy and amplitude. So right now in this simulation, I made damping or any kind of frictional stuff go to 0. Then when I send a wave, this amplitude remains the same as the wave moves across. It's which bead is moving, which bead has the kinetic and potential energy changes, but this amplitude remains the same. And that kind of represents some constant amount of energy that's moving along the string back and forth, bouncing back and forth. And once I include damping or some frictional forces, then you see this amplitude decrease over time, meaning the mechanical energy is being lost to thermal and whatever energy. Okay? So that amplitude is something you are actually familiar with. We didn't explicitly mention it last time, but you are familiar, or you should be familiar with the concept of amplitude from oscillation. So we are going to use that. So these are the 2 terms that you should already know or already have some kind of intuition for. I should introduce 2 more words that are probably going to be new. That's a way of categorizing different waves. We are not really going to do much with it, but I think if I don't mention them in class, then I'll be embarrassed in the future when anyways, you are supposed to know this when you have gone through this class, so let me discuss it now. It's a way of categorizing wave. So the kind of wave you see here right now, it's a very particular type of wave. It's one of the two different types of wave. So let me illustrate the other type of wave on this slinky. It's easier to do it on this slinky. So with this slinky, I can illustrate two different types of wave. Let's see. Can everyone see the slinky? It's not fading into background too much? Okay. So, oops. The wave that you are seeing on that simulation would be something like this. So this is one type of wave, right? You see that if I shake one end, then this sort of travels across the slinky. But that's not the only way. There can be a shaking here. I can shake this slinky this way, front and back, or I can shake this slinky left to right, this way. You see that if I do a little compression push, that push gets transmitted through. Like I make a small one pulse of this, and that sort of travels across almost to the end. And if I do this periodically, then you see something that's more periodic like this. So this is one version of that regular kind of oscillation, and this is another version of that oscillation I can give that results in a wave. So there's, and so the way you distinguish between the two is essentially the direction of displacement relative to the direction of wave propagation. So the ones that are easier to visualize, the ones that are easier to see, like in that on that simulation there, are the ones where the direction of displacement is perpendicular to the direction of wave propagation. So those we call transverse waves. So if you hear the word transverse, it's referring to that particular aspect of a wave property. When someone describes a wave as a transverse wave, as in that wave is a transverse wave, they are saying that wave velocity is perpendicular to, I think I kind of actually have to spell out, sorry. So when someone talks about transverse waves, displacement direction is perpendicular to the wave velocity. Wave velocity is in the same direction as the propagation direction. Does that make sense? Yes? So if I have this slinky, if I introduce any kind of displacement here, so I've been doing front and back, but I can actually be moving this in a circle. That's one way I could move it. But however I move it, this wave shape goes from left to right. So that's the wave propagation direction. And if I'm shaking this in a way that it's perpendicular to left to right, I could be moving it this way. Well, maybe not easily. So if it's perpendicular, that's a transverse wave. The other direction, is where the direction of displacement was along the direction of wave velocity, either in the same direction, or if you look at it carefully, sometimes you will see this moving backward. So when it's sort of parallel or anti-parallel to the direction of wave velocity, that's what we call longitudinal. So in a longitudinal wave, so we are still dealing with the same quantity. We are looking at the displacement direction is now parallel to the wave velocity. Good? And here's why I think so there are actually quite a few examples of longitudinal waves. The two most common ones that you should know are sound wave. So sound waves are longitudinal because the way sound is generated is through something like this speaker that you will see in your lab today. It's kind of a tiny speaker, but well, I guess I do have a bigger versions. So, one of the ways you can generate sound wave is with a speaker. And the way it works is I have this membrane, and there's something that's like a motor that's vibrating this membrane. And the vibration is pushing the air back and forth, and that's how sound waves are generated. And as this vibrates, it's causing the air molecules to move in this direction, and the sound waves propagate along the same direction. So sound waves is an example of longitudinal wave. And some types of waves come in both. Earthquake waves, there's a component of earthquake wave that's longitudinal. That's the P wave, or I think P stands for pressure wave. And there's a component of an earthquake wave that's transverse. That's the S wave. I think S stands for shear. So when you saw me do this to the slinky, where if I move this end in circle, actually you are seeing both types of wave. There's places where it's being compressed. That's the longitudinal wave. And where it's off from this line is where there's transverse wave. Okay? And most of the time, for the purpose of visualizing waves, we'll stick to transverse. Because with the longitudinal, sometimes it's difficult to see. See this important factor about wave. None of this segment of the medium that the wave is traveling in, it actually travels. So when I do it longitudinally, like when you look at this one ring, it'll move a little bit back and forth, but it never actually moves with the wave for a long distance. So, if you look at it carefully, you can see that. But that important fact about wave propagation that we looked at last time, it's easier to see with the transverse wave, because there the direction of displacement is perpendicular to the direction of wave propagation, so it's easier to separate them conceptually. So, but this is one wave categorization that I should have told you a little bit about. Now that I have, I probably won't really come back to this. Most of the waves that I draw, you will see them as transverse, and I'm kind of fine with that. But you should remember that the longitudinal waves do exist. Like sound waves that we are going to deal with in the lab today will be longitudinal waves.